So today I'm going to talk about how to make this graph neural net-based method for solving combinatorial optimization problem more powerful, more expressive. And this is work done in Georgia Tech and with a collaborator from Google Brain and also Chinese University of Hong Kong. So when we talk about this combinatorial optimization problem over graphs, and we can find many different applications. It doesn't matter what kind of area you're working on, a social network or internet or computational biology problem or smart city problem, you can find graph data. And very often you want to solve some graph-based combinatorial optimization problem, such as minimum Wallace cover problem, minimum dominant set, maximum dominant set, and then things like this, okay? So I will, in this talk, take a minimum Wallace cover as the running example, but we have tried the same method in other kind of combinatorial optimization as well, okay? Like maxcar and other combinatorial optimization. So let me just use this combinatorial optimization problem over graph as the running example. So in this particular problem, we want to select a subset of nodes from the graph. And if the node is selected, we're going to have a label 1. And what we try to do is to try to cover all the edges. So that means that at least one end of the edge is being selected, okay? So when you write it as a combinatorial optimization problem, it's going to be something like this. So every pair of every edge, and then for the two ends of the edge, the selection kind of indicator has to sum to be larger than 1, okay? And then you try to minimize the total number of selected nodes, right? And the problem is very simple, but it has been used in information diffusion, advertisement, and many different kind of areas. And it's very simple problem, but it's a NP-hard problem. And there are many heuristic or approximation algorithms being designed for this particular type of problem. And recently, there has been interest using something called graph neural net to parametrize and graph algorithm and learn this algorithm trying to solve this combinatorial optimization problem. So the kind of reasoning behind it is such combinatorial optimization problem are not just being solved once, but being solved repeatedly. There's opportunity to learn some algorithms which can adapt to that particular distribution problem, potentially solve better that combinatorial optimization problem. So what is graph neural nets? Graph neural net is something like this. It's a parameterized kind of graph propagation algorithm, graph message passing algorithm. For instance, this graph neural net want to learn some kind of vector representation for each one of these nodes in a graph. So initially, you can initialize this vector using maybe some node feature, okay, denoted as xi. And then this graph neural net is going to iteratively update these embedding representations for the nodes. And each one of these nodes is going to essentially aggregate the kind of messages or embedding from the neighbors. And after you finish aggregating, you're going to perform some kind of nonlinear transformation parameterized by some W1, W2. So you can think about this as a one-layer neural net parameterizing this message passing operator, okay? So using this as a neural net parameterized message passing operator, the embedding of each one of these nodes is going to be updated. Once you finish one round of updates of this embedding, you're going to carry out the second round and third round and the fourth round until you finish 2 rounds of update for these embeddings. So you can think about the number of iterations you run this neural net-based message passing operator. It's equivalent to the number of hops, how many number of hops you want to aggregate information from, right? So the larger the T, you can aggregate more information from a larger neighborhood, but it's also more computation intensive to run larger T. It will also create problem in chaining. I'm going to talk a little bit more about it. Once you have finished this T-step iteration, each one of these nodes is going to get some kind of vector representation. Then you can use this vector representation to parameterize some kind of selection probability. For instance, the probability whether that node should be in the solution set or not. So because this message passing operator is parameterized with W1, W2, but not fixed beforehand. When you train with the data, you will learn some massive population operators. So actually search over the space of parameter for this graph neural net, optimizing the GNN parameter. You can think about it as equivalent to search some kind of graph algorithms. Okay, so this is how you parameterize these type of node selection probability using the graph neural nets. Actually, using graph neural net, one can design two type of algorithm. One type is sequential algorithm. So in this case, you use graph neural net to parameterize the node selection probability. But when you are using this graph neural net based algorithm, you're going to sequentially select the node. So for instance, the first step, you're going to select this particular node using the graph neural net parameterize the selection probability. Once you select it, you can remove it, right? The incident edges for this particular graph. And then you work with the remaining graph, select the second one and remove the incident edges until all the edge has been covered. And there's another algorithm which you can parameterize by graph neural net is something called distributed local algorithm. So essentially, the selection of the node is not going to be carried out in a sequential fashion, but you are going to use these selection probability to simultaneously choose a set of nodes. And then you call this selecting node as a solution, okay? So essentially, decisions are made based on simultaneously and based on these kind of local graph property captured by these graph neural nets. So we have experimented with both this sequential algorithm and distributed local algorithm. I'm going to first quickly go through some examples of learned algorithm based on this sequential algorithm framework. I'm going to actually explain how to make graph neural net based algorithm more expressive using this distributed local algorithm kind of framework. So how do we actually learn this sequential algorithm? First, we're going to parameterize these algorithm choices using the graph neural net. And actually, the sequential kind of algorithm can be viewed as a Markov decision process. And you use this graph neural net to parameterize these node selection probability. And it's like in the language of reinforcement learning, that's like a state action value function, right? You parameterize it with these graph neural nets. Then you can actually use reinforcement learning to train this state action value function. So in the minimum waters cover kind of problem, we want to minimize the number of selected nodes. So every time you select a particular node, you're going to get a -1 reward. You want to select as few number of nodes as possible. You can use deep Q learning actually to optimize this state action value function. Once you finish training this algorithm, then actually you can apply it in a new algorithm and perform sequential selection for this new input graph instances, right? So that was a piece of work we did in 2018. And one thing that is interesting is to look at some of the algorithm learned by this graph neural net. So in this particular lattice cover problem, we have actually produced some animations for the learned algorithm on the leftmost panel. And then the middle one is going to be node greedy algorithm. You're going to select the nodes according to the degree of the node. You select the highest degree node and then remove the incident edges and work with the remaining ones. There's a two approximation algorithm, which is edge greedy. So every time you're going to select an edge. So the total sum, the sum of the degree of the two ends of the edge is going to be the largest. You select that greedily, okay? So I'm going to produce animation for each selection step. So you will see that the green edge are the incident edge of the selected node, and then the yellow node is going to be the selected node. So if an algorithm can solve the problem faster, it's going to clear out the graph faster, okay? So you find that initially this node greedy and edge greedy seems to be very good, right? It's clearing out the graph very fast. But near the end, you will find that actually this graph neural net based approach is able to finish the problem faster. Although the three graphs are exactly the same, just the visualization looks a little bit different. The reason why this is happening is the node greedy and edge greedy in some sense a little bit myopic. It's just performing the selection of highest degree node or highest degree edge in each iteration, but do not take too much into account the long-term effects of this selection. So essentially, this node greedy and edge greedy is breaking up the graph into lots of disconnected components, lots of small components. And then in the end, the algorithm is forced to select some node for each one of these components in order to finish the problem. But this a deep learning-based approach, graph neural-based approach, is able to select nodes with a relative high degree, but also make sure the graph is somehow connected, such that near the end, the later stage of the algorithm, this graph neural-based approach still have the potential to select one node and remove many incident edges and finish the problem faster. So sort of the learned algorithm is balancing a little bit between the degree of the node and the connectivity of the graph. So in the end, it's going to be faster, okay? So this is very interesting. Like this graph neural net-based approach allows you to search or discover some algorithm which is better than this designed algorithm. And you can adapt to a specific distributional problem instances, okay? So this is very exciting, and after we finish that, we are exploring how to make this type of graph neural net-based approach more flexible, right? And then actually to understand how to make such graph neural net-based approach more flexible, more expressive, it's actually easier to look at this framework of distributed local algorithm. There are more connection between the expressiveness of graph neural net to the existing algorithm, and the theory are better developed in that case. We're actually leveraging some of these understanding in the distributed local algorithm to trying to understand the expressiveness of graph neural net and how to design graph neural net-based algorithm which are more expressive. Okay, so distributed algorithm actually we have seen a lot, including the PageRank algorithm is some kind of distributed local algorithm, right? And in this case, in the PageRank, we try to learn one number for each one of the node in the graph. And then the score is produced by aggregating, in some sense, the rank from the neighboring nodes with the weights from the edges. And all these updates are carried out in a parallel fashion, okay? Distributed local fashion. And then graph neural net actually can express this algorithm. So it actually, if you compare this algorithm with graph neural net is like putting some additional nonlinear kind of operation on top of this aggregation step. And instead of learning just a single number, graph neural net is going to learn a vector representation. And on top of the vector representation, you can define other things such as selection probability, things like this, okay? So, so of course, this PageRank is hand designed, but the graph neural net is parametrized operator. Given you a distribution of input problem instances, you can actually learn the potential a new algorithm based on graph neural nets. So people also have studied the limitation in some sense of graph neural net in the kind of framework of the distributed local algorithm. First, in terms of the expressiveness of graph neural net, it can express algorithms such as Weisfelder-Lemon algorithm, approximate version of Weisfelder-Lemon algorithm, but it also exposes some of the limitation of graph neural nets. If you only run graph neural nets for t-hops, so it is only approximate version of Weisfelder-Lemon algorithm and many distributed local algorithm. And if you don't use t to be infinite, if you don't use very large t, you will never be able to recover the exact Weisfelder-Lemon algorithm. You will be always finding some kind of counterexamples which can break this algorithm expressed by graph neural nets. But if you use very large t, there's some problem with the learning of graph neural net, including it's very hard to train graph neural net. The gradient is hard to propagate through and optimize these GNN parameter. And essentially, this graph neural net is only able to capture local graph patterns. And without global information, it's just not expressing enough to handle some of the combinatorial optimization problem. And you need to, in some sense, give these graph neural nets a little bit of global information in order to make it more expressive and have the potential to learn more expressive kind of graph algorithms. So what I'm going to explain is some recent work for us in progress. And what we are going to do is actually, we'll try to enlarge the search space of graph neural net by augmenting the original graph with some cheap global feature, some global information which is easy to compute. For instance, something from spanning tree solution of the original graph. We have some kind of spanning tree approximation to the original graph, and we can compute some global solution based on spanning tree and other cheap information. We're going to augment essentially the original graph with some additional node feature and edge feature. I'm going to explain more. So after that, then you can actually parameterize your graph algorithm using graph neural net by taking into account these newly added global features. And then you can use supervised and unsupervised learning approach to learn it. There's some subtle kind of aspect to consider in order for the learning to be effective. Afterwards, one might also be interested in the question of which one of these augmented features are important for coming up with a better solution, and then whether this better algorithm is actually using some particular type of features in order to come up with a better solution. So we also have designed some kind of explainable model to actually explain which part of the augmented feature are more important for coming up with better graph algorithms. Okay, let me just go to these three block in a little bit more detail. So how do we actually enlarge the search space of GNN? Actually, the intuition we have is from some smart algorithm from the theoretical computer science community when they are trying to solve some large linear system. Okay. So essentially, you have some kind of graph problem. L is a graph Laplacian, and then you have a x, which is a vector you want to find. Lx equal to b. B is given to you. You try to solve such a large linear system. Okay. So if it's just a general kind of problem, the best known algorithm for solving a general linear system is n to the power of 2.373. But Keller et al. Designed a very smart algorithm which can solve the problem in near linear time. So the high-level idea is you're going to take a graph and then approximate it by some kind of tree structure. So in that case, they're approximating by something called low stretch spanning tree. Essentially, it's a spanning tree of the graph, but somehow the distance between two nodes are approximately preserved to some certain degree. Okay, you're making sure that the distance between nodes are pretty much preserved. There's also a near linear time algorithm to produce these so-called low stretch spanning tree. So once you have this tree approximation for the graph structure, so the graph originally is a grid, you approximate it by the spanning tree which contains this lucky edging. And then you can solve this linear system in near linear time, okay, on this spanning tree. And once you have the solution based on the spanning tree, then you are going to actually refine this solution using some kind of local updates, okay? So, and then you can show that you can essentially prove that the solution you get is with a very good computational complexity, okay, near linear time algorithm to solve this problem. So these actually inspire us to design this new kind of framework for making graph neural net based approach more expressive. So what we are going to do is exactly, approximating or generating graph with some kind of a tree structure. For instance, maybe maximum spanning tree or low stretch spanning tree, depending on applications. And then we are going to obtain the solution over these tree structures. Yeah. And then once we have obtained a solution, for instance, it's a minimum lattice cover problem. So these darker nodes are being selected. Then we are going to actually use this selected node as some kind of binary node features and augment the original graph with these binary node features. And also for the edges, there are edges present in this spanning tree edge, not present in the spanning tree, we're actually going to also add this binary kind of feature to the edge as well, okay? So you can imagine there might be multiple different type of spanning trees on the same graph. You can actually run multiple spanning tree algorithms on the same graph and then produce the solution on these different graphs. And then you can augment essentially each node in the original graph with a vector, right? Of a binary vector, whether the particular node is included in the solution of a corresponding spanning tree or not. Similarly, for the edges, you can also add a binary feature vector to it, right? So once you have that,
5 minutes left.
Sorry?
You have 5 minutes left.
Yeah, and then essentially, once you have these augmented graph structure, right, and then you can just run graph neural net on top of it. You can actually also include the greedy solution on top of it as well. And what you will find is with this augmentation, and you just learn your graph neural net based algorithm, it's actually doing very well, okay? It's much better than some of the other approaches people have thought about before of augmenting the graph structure, including one-hot vector augmentation and random feature augmentation. And this global kind of information-based approach is able to augment the graph and give you, allows you to learn graph algorithm, which much better, much better approximation ratio. So in terms of learning, you can imagine there can be supervised learning, where you actually take the graph and then compute its exact solution and use that as a supervision to train your graph neural nets. So I'm not going to go too much into details of this approach. There's some subtleties. But recently, there's a new technique coming up in NIPS, which allows you to train graph neural net-based approach or deep learning-based algorithm using unsupervised approach. You can actually have these objective function, which takes into account, is a little bit like an augmented Lagrangian, takes into account the objective function and constraints, and actually use unsupervised learning approach to train this graph neural net-based approach. And this allows this graph neural net-based approach to be trained with much, much larger graph structures, okay? So what we find is it actually allows us this unsupervised learning approach, DADU, also give us very good algorithms across different size graphs and much better approximation ratio compared to other even more sophisticated LP relaxation and other approximation algorithms, right? So also this graph neural net-based approach has a better, in some sense, time solution trade-off. So this graph neural net-based approach is somewhere here, hidden in this purple one. The lag and lag U are the supervised and unsupervised approach. It gives you some approximation ratio close to 1, but the runtime is faster than these pink ones, which are produced by Groby and this kind of exact solution. Okay. So last, I just want to briefly mention about this explainer kind of approach for understanding which part of the feature is going to be the most important. Which one is augmented feature is important for learning the better algorithm. So I mentioned earlier, we use graph neural net to parametrize the selection algorithm. It's producing the probability whether the node will be selected into the solution set or not. So what we are doing is we are actually going to build the explainable model, which try to explain, for instance, if these nodes are selected, what is the substructure around this node, and what are the corresponding features which allows the graph neural net to make the decision this node should be selected or not selected. And this explainer model is again based on graph neural nets, and it's actually taking a graph around this particular nodes, and it's running the second graph neural net model to define, these selection probability of these particular node feature or edge features. And then this explainer model, graph neural net, can actually be optimized using mutual information to, and the when we learn a particular algorithm, we actually also learn an explainer, which can explain which part of the feature, augmented feature, or which one of the substructure is making a critical contribute critical information for making the decision. Okay. So what we find is, for instance, for the meaning versus cover, we learn this distributed local algorithm. The explainer is actually able to show that the learning algorithm is something like a node greedy. Okay, so it's actually selecting these edges around a particular node, and these edges around a node is actually the important information for determining whether the node should be in the solution set or not. So actually, for this explainer we produced by this approach I just explained earlier, it's doing much better job in terms of explanation comparing to another recent kind of explainer approach called a GNN explainer. And GNN explainer has some tuning parameter there. And depending on tuning parameter, you get some explanation, which is hard to understand what the algorithm is doing. Besides that, the explainer is also able to discover some anchor node in the graph where it is very important for these nodes to be present such that other, to explain why other nodes are being selected. So this is some kind of anchor node, which sort of is important in the entire graph. And the relative information about other nodes to this anchor node determines whether the node should be included in the solution set or not. So this is the second last slide. So as I mentioned earlier, this explainer algorithm is also able to help us understand which one of these augmented features are important for the algorithm, the graph neural net-based algorithm to learn a better algorithm. For instance, for the minimum versus cover problem, we have augmented the graph with different type of greedy solutions, node greedy and edge greedy. And then based on spanning tree, we run some solution. And we also have a weak two coloring as some kind of the solution of the weak two coloring problem, and augment that solution to the node feature, also random feature. So the explainer is actually able to pick out the node greedy and tree dynamic programming is the most important kind of feature to use to augment the graph, such that you can learn a better graph algorithm. So for other problems, you will find that different type of node feature, augment feature are important. Okay. That's pretty much about this framework. So the sort of the high level idea is this graph neural net-based approach is very local, right? It only captures local graph structure, and it won't give you. It actually has some limitation in terms of learning an expressive graph algorithm. So in order to make it more expressive, we can augment the original graph with some very cheap global features, and then run graph neural net-based algorithm on top of that, and learn it with either supervised or unsupervised approach, and you're able to get better graph algorithms. And with our framework, you can also explain a little bit what are the important features to provide a particular decision of the graph neural nets. That's what I want to talk about, and we have time for question.